Hi everyone, I'm Joanna and I am a PhD student in the Gianeschi lab at Northwestern. And today I'm going to tell you about my research studying organic solvated polymeric nanomaterials with liquid cell transmission electron microscopy. So to study nanomaterials in organic solvents, we first wanted to design this multimodal study to really understand how our electron beam can interact with these different solvents. And so first off, we designed these Monte-Carlo simulations that kind of tracked electron trajectories through different liquid layers composed of different solvents. And so the solvents that we specifically chose to investigate are water, methanol, and DMF. And so to conduct these studies, we created this simulation design where we were specifically looking at the 50 by 50 micron viewing region that is typical for liquid cell experiments, and we looked over a range of liquid thicknesses from 100 nanometers to 10 microns. And so from these Monte-Carlo simulations, we can extract a lot of meaningful parameters, but we decided to focus on a subset of the data that is generated from these types of simulations. And so first off, we looked at the secondary electron generation, which kind of gives us a way to assess how much secondary damage is happening to the solvent that can then go on to degrade your sample. And so as you can see from this plot, over the range of liquid thicknesses, all three solvents, methanol, DMF, and water, behaved pretty similarly, but at higher liquid thicknesses, DMF did surpass methanol and water. And so we found that this parameter actually trended with the molar concentration of these pure solvents. And at the liquid thicknesses that are most useful for liquid cell experiments, the secondary electron generation wasn't a major contributor to solvent damage. And so next we looked at the absorbed energy and the absorbed dose, which kind of give us different ways of evaluating how much energy the electron beam is losing as it penetrates through these different solvents. And so first off, for the absorbed energy, you can see that water surpasses the two organic solvents, and we found that this parameter actually trended with the density. And so this is somewhat unsurprising that a more dense solvent may be less amenable to liquid cell TM studies and will cause the electron beam to lose more energy. And then finally, for the absorbed dose, which is measured in grays, and to remind everyone, grays is a unit that is expressed in joules per kilogram, we found that once again, water surpassed the two organic solvents. And this was pretty interesting because actually this outcome trended with the elemental composition of oxygen in each solvent. And so oxygen is the heaviest element found in all three solvents. And so it's unsurprising that a unit that is expressed in grays should trend more with these heavier elements. And so again, that meant that water had the highest absorbed dose, followed by methanol, and then by DMF. And so taking all of these parameters together, what we determined is that overall, these suggest that perhaps organic solvents are more amenable to liquid cell TM studies, especially if we're considering the absorbed energy and the absorbed dose. And so while from a scattering perspective, we gain a lot of meaningful insight, we wanted to complement that scattering insight with actual chemical insight. And so to do so, we designed these COMSOL radiolysis models that evaluated how the electron beam degraded these different solvents that we were interested in. And so for this, the model design is shown here. So we were tracking the concentration with time of different radiolytic products, and this is dictated by the sum of these individual reaction rates with adding in the G value, which is the yield due to direct irradiation. And so in each solvent, we generate a lot of different radiolytic products, and here there are a subset of the possible radiolytic products shown. And so you can see that for all three of these solvents, we generate some radical and molecular products, and some of them are common to these different solvents. And so for the radicals that are unique to each solvent, we can kind of rank the different reactivities just purely based on their chemistry. And so hydroxyl radicals, which are unique to water, are the most reactive radical species generated in any of these solvents because you have a radical that's centered on an electronegative atom. This is followed by methyl radicals and then by the secondary and acyl radical generated in DMF. And so here, based purely on radical reactivity, we can say that water is probably the least amenable to liquid LCTEM studies and will cause a lot of secondary damage to whatever sample you're trying to study. And then finally, looking at the steady state concentration of these radicals that are unique to each solvent, you can see that the lowest reactivity radicals, which are generated in DMF, have the high steady state concentrations. So overall, this suggests that DMF has kind of intermediate stability. And this is followed by hydroxyl radicals in water and then by methyl radicals in methanol. And so overall, putting this fully together, it seems that methanol is the most amenable to liquid LCTEM studies because while you are forming an intermediate reactivity radical, you are forming the lowest amount of it. And so moving forward to kind of complement and explain the simulations and models, we wanted to create this multimodal study where we could use liquid phase EM in tandem with some sort of post-mortem technique to really prove that what we were seeing in these simulations and models was in fact accurate. And so to do this, we studied this model system, polystyrene block poly4 vinyl pyridine. And this is a polymer that is commonly used to make different types of films, and that is because of its really interesting phase behavior in different solvents. And so we again investigated the same solvents that we investigated with the Monte-Carlo simulations and radiolysis models, so methanol, water, and DMF, and we studied this polymer in those different solvents with liquid phase EM and used MALDI-IMS to evaluate the sample integrity after imaging. And so what we can see here is in the dry state, these worms that are formed in methanol from this polymer, you really see a tangled mess, and it's unclear whether this is a drying artifact or really reflective of the native sample morphology. And when we look at the sample in liquid, we can see that in fact, yes, this is not a drying artifact, and we really do have this network of worms. Next, in DMF, we see that we have these micellar nanoparticles, and in the solution phase experiment, we can only see the larger particles, though we are still able to kind of make out these features. And then finally, in water, it's unclear whether this is a drying artifact or really reflective of the morphology. And so when we conducted the liquid phase EM experiment, we aren't really gaining more insight. We can't really clearly make out these features. And this agrees with what we saw in the Monte-Carlo simulations because we have poorer contrast in these denser solvents, whereas in methanol, we are actually able to differentiate more of these features. And all of these studies were performed with our Poseidon holder. And so to evaluate the sample integrity under these different imaging conditions and kind of confirm what we were seeing by those radiolysis models and Monte-Carlo simulations, I mentioned that we were going to use MALDI-IMS. And so the way that a liquid cell TM experiment correlated by MALDI-IMS works is first you do your liquid cell experiment, so you pipette your sample, assemble the liquid cell, and image it as you ordinarily would. And then after the liquid cell experiment, you conduct MALDI-IMS, where first you pry open the liquid cell chips and allow the sample to dry on the surface. You coat the surface with matrix using a matrix sprayer. And then finally, you raster this laser across the surface of the liquid cell chips and generate mass spectra at every point. And so by using this protocol, you can evaluate whether your sample survived or underwent degradation under different imaging conditions and ultimately create these mass filtered maps of the liquid cell chip surfaces. And so here we looked at a lot of different conditions. So first off, we looked at each of the solvents that we were interested in, so methanol, DMF, and water under either low flux conditions and high flux conditions. And so what you can see here is that under low flux conditions in methanol and under high flux conditions in methanol, we have complete signal retention. So our overall signal intensity is identical to the signal intensity in an unimaged control sample. Likewise, in DMF under low flux conditions, we have complete sample retention and we don't seem to have any degradation. However, the samples seem to be damaged in DMF under high flux conditions. As you can see, we have a way lower signal intensity of our polymer distribution. And then in water under low flux conditions, we actually had selective degradation of the polystyrene block, and the peak spacing that's left corresponds to the poly4 vinyl pyridine block. And then under high flux conditions in water, we have completely obliterated our sample entirely. And so in these mass spectra, we were looking at specifically the window region. And so you can also get color mass for the entire liquid cell chip, as you can see on the right side of the slide. So we have the entire surface map of that chip, and then we can also specifically look at that window. And so overall, the results that we obtained from this study show us that, in agreement with our radiolysis models, it seems that methanol is, again, the most amenable solvent to liquid cell TM studies, whereas water is less suited to liquid cell studies, and DMF shows intermediate stability. And so finally, with all of those results in hand, we are interested in whether we could actually probe the dynamics of these types of systems in organic solutions. And so based on the MALDI-IMS results we obtained on the last slide, we knew that we had to limit our electron flux conditions for systems where we had DMF, whereas with methanol, we could, image the sample at higher fluxes. And so we designed this solvent switch study with our protochips holder, where initially we had our sample in methanol. And so if you remember from a few slides ago, in methanol, this polymer forms these worms. And so you can see that we have this kind of faint network of dispersed worms initially. But upon flowing in DMF, we begin to form these micellar nanoparticles off of these worms. So in that intermediate time point, you can see that we have worms and micelles together in the liquid cell. And then finally, upon flowing in further, for a total of 20 minutes, we have a pure micelle phase in liquid. And so by designing this multimodal study, we were ultimately able to probe the dynamics of this type of system. And going forward, we thought that this type of strategy of using Monte-Carlo simulations, radiolysis models, and liquid phase EM in tandem with postmortem analysis would be really useful for looking at these types of complex transitions. And so to conclude, overall in the study, we created a kind of general workflow for analyzing different materials in the solution phase. And by designing this rigorous multimodal study, we were ultimately able to create conditions that would allow us to observe this solvent switch transition. And so going forward, one of the things that we're interested in our lab is, can we actually look at dynamic systems in organic solvents? Are these actually more amenable to liquid cell TEM because of the increased stability of these solvents under electron beam irradiation and the lower density of these solvents often compared to water? And so with that, I want to thank the Joanna group and everyone for their attention.